Hello everyone, my name is Chantel and welcome to this Aldic Active-HDL video where I'll be showing how to utilize the FSM Testbench Generator alongside FSM Coverage. Active-HDL allows the user to create FSMs through the state diagram editor, simplifying the FSM making process while also generating the HDL code for the FSM. This tool also allows for the auto-generation of test benches for the FSM. This, plus FSM Coverage, becomes this comprehensive package for a streamlined design and verification process for FSMs. So now I'll go ahead and start with the example design. I have this design called Data Path opened. This can be accessed by going to the Help tab, Open Example, VHDL Designs, and it's here. In this design, there's already an FSM made for the control. And as a heads up, I'm going through this demonstration under the assumption that you're already familiar with the FSM Editor and a bit of FSM Coverage. If you aren't, I've already made 2 videos about it, and they'll be linked in the video description below. Now to generate a test bench for this FSM, head over to this FSM tab and go all the way down to the Generate Test Bench option. Clicking on it opens up a new window where you'll choose what strategies to generate test benches from. Strategy 1 generates a test bench that just goes through all the FSM states. It's only dedicated to going through the machine states, so testing for transitions and sequences won't be comprehensive. Strategy 2 creates a test bench that tests all of the machine's transitions. While this is focused on just verifying transitions, this strategy also inherently covers going through the machine's states like in Strategy 1. The third and last strategy contains the stimuli needed to test transitions from each state of the state machine to the reset state of the state machine. Once the targeted state is reached, the reset condition is forced, bringing the machine back to the reset state and transitioning to the next targeted state. This process is repeated until all states have been reached through this method. This strategy tests all resets specified and is used to verify only synchronous machines. It also implicitly covers the test vectors from Strategy 1. For this demonstration, I'm going to generate all 3 strategies, so I'm keeping all of them checked, and now I'll click on Generate. You can see in the console window that the test bench generation is complete, along with a quick summary of the test quality of each strategy. In the design browser, there's now a new folder called Control FSM TB, where all 3 generated strategies have their test bench code, as well as their own macro to run the test bench. All of the macros for each test bench have an identical layout, with the only difference being the test bench that's being simulated, indicated by TB1, TB2, or TB3. In these macros, only the FSM and the test bench are being compiled with code coverage. Then simulation is initialized with ACDV coverage, the waveform is also added, and finally the simulation runs and the code coverage report is created. Now going to the test benches, starting with test bench strategy 1, we can see with the help of the comments that this test bench tests for all states. And we can confirm as we scroll through the code that each state is attempted to get transitioned to. For strategy 2, we can see that it tests for all transitions, starting with the transition from start S into start S again, and continuing with the different transitions from there. And lastly, for strategy 3, we can see how the states transition all the way up to the add state, where the reset signal goes high and brings the state machine back to start S, and from there, it just transitions to the next targeted state, which looks to be add only, before repeating the process of setting reset high and going back to start S. Now that we've seen how each strategy works, let's go through some FSM coverage. When we generate the HDL code for the FSM diagram, FSM coverage can be included by going to the FSM tab, Code Generation Settings, and clicking on Enable FSM Coverage. Click OK to confirm, and then click on the Generate HDL Code button in the FSM Editor toolbar. Now notice how a new VHDL file is created underneath the FSM. In this VHDL code, all the FSM coverage pragmas are located right before the state machines code. And now we can take a look at FSM coverage pragmas. Since this is VHDL code, I'll only be using ALDEC proprietary pragmas. From the code generation settings, the pragmas for the current state register, initial state, legal states, and legal transitions are defined. When it comes to defining states, transitions, and sequences, there are only two ways you can go about doing so. One way is to define all your states, transitions, and sequences that you want to include in the coverage collection with state, trans, and seq pragmas. If no trans or seq pragmas are specified, then all the possible transitions and sequences will be automatically generated based on available legal states and transitions. All other components not defined or generated in these ways will be excluded from coverage computation. The second way to define these components is by using the ignore pragmas for trans, state, and seq. In this case, coverage will be collected for all available components except for the ones specified using ignore states, ignore trans, or ignore seq pragmas. If you define some components with the ignore pragmas while also having state, trans, and seq pragmas, the ignore pragmas will have no effect. For FSM coverage, you can also define illegal states, transitions, and sequences. These components will be marked as illegal and are removed from coverage computation, but they will have their own section in the coverage report. I'll first run through all three test benches using the default generated pragmas for the states and transitions. I'll also define a sequence, but before I do, I'm just going to make sure I have right permissions for the code by right-clicking on the VHD file and going to its Windows Explorer properties and unchecking the read-only attribute. Then I'll apply the setting and click OK. Then in the code, I'll define a sequence using seq and define this sequence as start s into res ALU1 into add only and then into add only again. Next, I'll go and edit each test bench to only do FSM coverage and have them all compile the VHD file of the FSM before running them. And now I'll first run the Strategy 1 test bench. We can see our waveform results, and now we can open the coverage report by going to File, Open, and in the Designs source folder, I'll look for an HTML file for TB1 and open that. In the cumulative summary, it shows that all the states have been hit, but some transitions and the sequence I defined were not hit at all. Next, I'll go ahead and run the Strategy 2 test bench. Now, when I open up the coverage report for this strategy, the summary shows that 100% of the states, transitions, and sequences defined have been hit during this simulation run. This makes sense as this strategy tests for all transitions, which made it likely to hit the sequence I defined as well. Lastly, I'll run Strategy 3's test bench. For this report, the results seem similar to Strategy 1, and notice in the console that undefined transitions of the states going into the initial state were detected. In the detailed report of the FSM coverage, we can see that not all transitions were hit since transitions aren't the main purpose of this strategy. Notice also that some transitions were hit a lot because of the reset signal, And so a transition such as start S into res ALU1 would be hit frequently as this strategy resets after a targeted state has been reached. So that was the FSM coverage method by explicitly defining components. Now I'll show FSM coverage by defining excluded components. In this case, I'll keep everything up to the defined states, but I'll remove all the transitions and just define and ignore trans of LD out into start S. I'll also add an illegal component, and for demonstration purposes, I'll define an illegal transition as start S into start S. With my new set of pragmas, I'm going to run a simulation using strategy 2. Notice that a warning is shown in the console of the ignored transition being detected, and it also shows an error saying that an illegal transition was hit. So let's go see how the report turned out. In the cumulative summary, notice that the number of transitions and sequences being covered has increased substantially. And in the report info, the test details is red, meaning that there was an error, and that error was, in fact, the hit on the illegal transition. Now let's go to the FSM's full coverage. All the states were covered with this strategy, but by defining only excluded components, this strategy barely covered the transitions and didn't hit any of the 1000 sequences. Notice that there's a section for illegal transitions and shows a report that it was hit once, but it's not part of the coverage computation. Illegal states and sequences would have their own section as well if they were defined. And lastly, notice that the undefined transition was detected as seen in the console warning, but it's nowhere to be seen in the coverage report under transitions. And that concludes this video on how to utilize the FSM Testbench Generator along with FSM coverage. The Testbench Generator speeds up the process of testing an FSM, and you could further verify its logic through FSM coverage pragmas embedded into the code. With the variety of strategies and pragmas you can use together, you'll be able to effectively expedite the FSM verification process. Thanks for watching.